Okay. So now we're on to...
Can I ask you one
Yes.
question? Why did we divide 6 by 4?
In what?
Tan inverse.
Because the opposite was 6 and the adjacent was 4.
So the opposite was 6 and the adjacent was 8. The base.
No, 4.
Oh, why do we have to have?
Explain it to him.
Because the angle is here. We calculate the angle. This angle. No, not that angle. In three parts in here.
Oh, so we're calculating this and this.
Yeah.
Oh, okay.
Okay. Next lesson, if you can write this down.
Oh.
Will we get 3 lessons done today?
How many pages do they need?
These aren't big lessons.
Yeah, we can finish. Fingers crossed.
Leave me alone. Okay, now, work. You got that?
No.
Yeah, okay. Right, so, in this picture, ready? In this picture, work is being done. So what things do we need for work to be done? So if you want to say something is doing work, what things do we need? And have a look at the picture. Yeah, so the man has a force. That's one thing we need. What else would we need?
Time.
Yeah, energy, distance. So, firstly, you definitely need a force. We're all clear with that. But also, we need a distance because he's moving the dirt. And if he moves the dirt more, that's more work. So there must be a distance involved. Anything else? Maybe a mass, maybe a time, and also maybe an area as well. So force and force making something move, and there must be some kind of movement. So really, it comes down to usually just a force and a distance is what you need to say that there's work being done. So the definition of work as a physics term is work done by a force acting on a body is the force along the direction of the displacement multiplied by the displacement. So in other words, simply put, as a formula, force or work is force multiplied distance, where W is work, force is F, and S is the displacement, the distance. Actually, really, I should say distance rather than displacement, but whatever. Okay, so clearly the units for work is what? Newton meter is the units. The units used are joules. Now, a joule is actually just 1 Newton meter. 1 joule of work is when 1 Newton is applied over 1 meter. The same thing as 1 Newton meter. Okay, there's a lot here to write down. You could be asked this in the exam, and they have asked this in the exam.
Of the distance, not the displacement.
I should really say distance, I believe, rather than displacement. But like I said, whatevs.
But displacement would be right.
No, better write down distance. It's weird because it should be FD, but in the formula book it's FF. And I think the formula book says displacement, but I'm pretty sure it needs to be a distance. But 99% of the time, distance is displacement. So, like I said, whatevs. Okay. Did you write all of this down? Did you, Lee? Okay.
I have a question, but I'm not sure I should ask or not.
Will it make me angry?
No, but...
Then ask away.
Okay. I asked Miss Lorraine about this. We're doing the ESAP with her.
Cool.
Okay. So here's the question.
Yes.
It's about natural causes that are affecting the planet Earth. Okay. What I thought about was if the mass of the planet increases, would that not affect the gravity, the force of gravity?
If the mass increases, it
Yes.
would affect the force of gravity.
Yes. Okay.
If it increased.
Yes, and that would change the things around planet Earth, like
It would change
distances.
its movement, yes.
Okay.
Yes.
So the question is, the mass of Earth, of planet Earth, let's say millions of years ago, and today, is it the same or does it change?
The mass changes, but so little. The only reason the mass would change is if something landed on the Earth from outer space, like a rock,
Yeah.
but a rock is quite small compared to the size of the Earth, and also the mass would decrease when things leave the Earth, such as a rocket.
Yeah.
So you know there's space stations in orbit. The mass of that space station came from steel and iron from the Earth's core. So the mass slightly decreased when the rocket left, and slightly increased when a meteor or something small lands on the Earth. In total, I would say the mass has not changed because it's too small to make any difference. Too small.
So the population or all of those would not affect the mass?
No, because the mass of the people must have came from the planet, in the planet. So, you know, when you eat a cow and build muscle from the protein, you're just taking the mass from the cow. And where did the cow get its mass from? From the grass, which came from the earth. So in total, it's the same. Yeah. Okay, continue. You have this? Oh, come on.
I was listening to you.
He's-
That was my theory of it.
What? My answer, or
Yeah, your answer. That's
how on earth did this come up in ESAP though? Like, what were you talking about?
She was giving us the topics about the
Natural.
the coursework for chemistry. One
Ah,
of the topics were natural,
climate change.
natural causes of climate change.
Mhm.
I was thinking that we can't stop this, and it's not being applied by the human, so it's a natural cause.
Too small to count as a cause.
Yeah.
Even babies are like made because of the food.
Yep. Everything, yeah. It's conserved. It's not changing in total. The mass had to come from somewhere, and it didn't come from space. Most babies don't come from space. So they were built on Earth, using the mass on Earth. Superman being an exception, of course. Of course. We all know Superman. And he's only one exception. Alright, continuing. Right, so here is a simple question. I don't need you to write this down because it's not a calculation, it's just to think about work. Where and what is doing the work in each of these examples? That is, what has work done to it? No, I'm sure that was wrong type in there. What work was done to it, not what has work done to it. No, it's wrong. What work was done to it?
What?
Yeah, delete has. It should have been what work was done to it.
What
Okay.
three what are all?
This should say what work was done, not what has work done to it.
But work is three letter or four letter?
It's true, usually WAS. Yeah. What did you think it was?
W-E-R-E.
Were. Was. Yeah. Okay. A mother lifting her baby up from the ground. What is the work being done?
The baby being lifted.
Yeah. The lifting is the force. And the distance from the ground. Yeah, the height. Yeah. A woman pushing a large box across the ground. The pushing force, and the distance is the amount across the ground. Yeah. A man kicking a football. Now wait, think for a moment before you give me an answer, Faisal. So, a man kicking a football. So what is the force?
Kicking.
The kicking. And the distance?
It's like more.
So tell me from where to where then?
No.
No.
No, it's the whole thing. It's not
The range.
designed- Yeah.
The project
No.
of the ball? No. I'm not getting the football.
So we have two good but wrong answers.
Until the ball stops.
Hmm?
Until the ball stops.
The distance from him till the ball stops? No. No, there is a distance.
The distance after.
Not until he kicks. No, not this one. Yeah?
Attempts to kick the ball continues with his leg.
We're getting closer now. I think that you have it here. The distance is the distance the ball travels while his foot is in contact with the ball. In other words, while the force is applied. So, if he kicks the ball,
That's
the
a small
distance, yes, but that's the distance. It's the distance while his foot is touching the ball, but only while it's in contact. Not the distance before, and not the distance after. The difference during the kick. So as you said, when his leg swings, it's this distance. A child hitting the wall. What's the force? The hitting force. And the distance, again, think, no. You're doing that thing where you don't think.
The distance when he touches the contact with the wall.
Skin. how
Yep,
far
that's
goes
it.
in.
That's it. How far the skin compresses,
Mhm.
which is a very small distance. Yes. Yes? What? And lastly, a father carrying his child, so on his shoulders, and the father is walking.
Carrying.
The force is the force he provides to keep the child up. But what is the distance?
The contraction between the child's butt and the father's skin on the shoulder.
Very good. So the distance is the distance, but it's actually a bit more than that because it's the force, but while he's walking, the distance is slightly moving up and down. So it's all these little work jobs. Plus there's other things, there's other work as well being done. So what is also trying to happen is the child is pushing down on the father, so the muscles in the back need to be pushing up, so these muscles are also, contracting as well. There's actually a lot that's happening here. What it's not, if you think about it, it's not this distance he moves horizontally, because where's the force? The force is being provided upwards, so it has to be some distance vertical, not horizontal. Do you understand?
Horizontal is like the balancing.
The horizontal is not interesting here because this isn't. I suppose you can think about it like this: if the father stands still and holds the boy, or not if he kind of just walks slowly, or if he walks fast, it doesn't change how much work he's doing. Because the work is holding the boy up, not the movement horizontally. I know it's kind of hard to picture because you feel like if he walks further with the child, that's more work. But it's more work only because he's holding the child up longer, not because he walks further.
So time has to do with it?
Time is something that we'll use later, but not right now. So right now we are just talking about work, but time will come into it later as something else. Okay. The last example was interesting and we talked about it. Blah, blah, blah. Right, now we have some actual calculation ones to do. So you can write or draw this and then I'll do it. So write or draw, please.
Don't smooth surfaces provide friction?
No.
Like how smooth?
In physics, can never be frictionless, but in physics, whenever we describe a surface as smooth, it means no friction. Okay, did you write or draw this yet? Got that? Now, part ABC, listen, ABC is old, DE is new. ABC you can do for me right now because it's just UVATS. Yeah? What do I want in A? Acceleration. What do I give you?
Speed and time.
I give you U, V and T. Part A, I want A. Part B, I want S. Part C, I want F. How do you get F? F equals MA. So ABC, do for me now. I'll do D and E. I want ABC now. Okay, have we got ABC? ABC? Yep, okay. So, what did you get for the acceleration of the block? Okay, I'm going to go with the majority here. Sorry to tell you that. So you got A is 0.2 meters per second squared. And what did you get for the distance it travelled? What did you get? 5 meters? Huh? 2.5. You forgot the 2 in your formula, didn't you? Well, look at your formula for v squared. What did you write down?
2.5.
Did you write down v squared equals u squared plus as?
No.
You wrote something else down?
No, it's just
Oh, well then. What did you get?
2.5.
2.5. And then finally, for you, what did you get for the F, which was MA? 20 newtons. Now, if she's pushing this, the work that she did in pushing it, so this is part D now, work is force times distance. That's 20 times 2.5, which is 50, and the unit? Joules, or Newton meters, yeah. Now, part E, what do I ask here? The same force, but at an angle of 10. So this time, it's the same force, but at an angle of 10.
20.
So we only care about the work done this direction, which is F cos 10. So will that be more work or less work?
More.
Less. Work is force times distance, which will be F cos 10 times 2.5. And actually I know the F, so I should write it in. So what do you get now, please? 50 times cos 10, I suppose. Uh, 49.2, thank you. Joules.
Can you go back to the calculator?
Okay.
No.
Didn't trust me?
No, you trust my eyes.
Okay. Huh?
Where is it?
Right in the question.
But why the box is not the horizontal?
Yeah, she says 10 degrees to the horizontal. So this here is 10. No?
What's the answer for the
49.
49.2.
So if we push the box with an angle, we'll use less.
Let me explain.
100 kg?
Guys, can I explain something now? Vice was just asking me, which is with the last part, okay? So, think about this. If you're the person pushing this block, in the first situation you pushed it horizontally, and in the second situation you pushed it at an angle, but with the same force, 50 newtons and 50 newtons. So, for you, you're doing the same amount of effort, but
The work done exerted by the box is less.
the work on the box is less. The difference is, how can I put this? Just up the side here. Here's the two situations. Yeah. When you push horizontally, or when you push at an angle, you have to do the same amount of work. I don't know how I can draw that. You're doing work. There's you doing work. Yeah, it does look like smell. You're doing the same amount of work. But the block will have more work done to it here and less work done to it here. I was very careful with my choice of English here. I said how much work was done to the block, not how much work did you do, because in both cases you're doing the same thing, but the block gets more done to it first time than second time. So you might be wondering, okay, well, if this has less done to it and this has more, but you're doing the same, then where has the extra work gone? Yeah, a couple of different places, like pushing the block up slightly from the ground reduces the friction slightly maybe, or just makes your hands hotter. You know, in other words, it's almost like this is wasted work, which we don't care about.
But then there's no friction, so...
On the ground, true, but not on the face of the block maybe. Maybe, you know, you're wasting energy pushing up the block, yeah. Anyways, that's not really too much to concern ourselves with right now. Right, there is another element at play. So, why does standing on one foot feel more difficult? Yeah, but why would that matter?
The pressure increase.
Yeah, but why? What is pressure? We haven't talked about pressure.
Have you heard forces acting on less area? There's more...
The same force, but...
More distance?
Less area.
No, less area, yeah? So, you're the same weight, but you're what about if you stand on one toe?
You can.
You can't.
Ah, you can. These people do it all the time. Yeah?
It's not one toe.
That is one toe.
That's
Okay.
big of a toe.
One big toe and maybe one small toe. It's not much.
No. It's all the toe, but not
Alright, fine. What about if you were standing on your toes?
Yeah.
Okay. So, there's another element at play here. Not only is force important, but also the area. Because if you make the area smaller, that hurts more.
What about the distance? Like, because like if you're standing on one foot, then it will be compressed more. Like, isn't the distance going to be slightly bigger?
We're just talking about I know we're talking about work and all that, but just right now we're talking about pain. So force on a smaller area will be more painful than on a big area. So this gives us the need to define something new called pressure. which is just how much something is pushing on something else. More technically, pressure is defined as force over area. So what is the unit for pressure? Here it's newtons per meter squared, which we call a pascal. The units are pascals, where we say 1 pascal is 1 newton per meter squared. You got this definition? Yes, continue. I don't know if sitting there means not bothering to write the definition down, or you just wrote it down really quickly. Yeah. Okay. Alright, okay. I don't know. Should I trust you?
Right angle.
Yeah, the force is applied to the area at right angles.
The force is applied to the area at right angle.
Force and area are at right angles in the diagram. Like this. This is the area, this is the force.
So,
Perpendicular. Right angles means perpendicular. Yeah. Anybody watch the Super Bowl?
You don't want to know.
Huh?
Could
You
you
saw
watch
the last point?
No, that was too late. I only watched the first half until 2 a.m. Then I went to bed.
First half was 24-0.
24-3.
Then 32.
Yeah.
Then it was at some point, I think 28.
Was it?
Yeah.
But they
They
still,
scored first,
but
and
they
then
still
we-
won.
That's
Yeah.
it.
Would have been exciting to watch, but it would have been between 2 a.m. and 4 a.m. So
I had a friend at the stadium watching it.
cool. Which team were they?
That's it.
Nice, nice. Okay, continue. Right. So let's have a look at an example. It's the same example as earlier, but this time I want the pressure on her hands, and her hands are 100 centimeters squared. Is it though? I don't think so, because 100 is only 10 by 10. 10 by 10 is not that big. Dudes, give me the ruler.
It's more than
14 by 6 for me, roughly.
So 20.
So I'm 84.
Yeah, she's a woman.
Yeah,
It's a big woman.
It's a Viking.
yeah, Viking, yeah.
Valkyrie.
7 by about 15 maybe.
Up your hand is increasing it.
Okay, well I'm not measuring it exactly, I'm just... 100 seems like a reasonable number. Yes, excuse me for not measuring it exactly. Right, so let's calculate the pressure here. Pressure, yeah, well what's the formula? Pressure is force over area, and the force is, was it 20 newtons? And the area is,
0.1. No, not 0.1. We have to change the square too.
Yeah.
hang on, let's calculate. 100 centimeters squared is 100 centi squared meters squared, which is 0.01 squared meter squared, which is 100 times 0.0001 meter squared, which is 4, 1, 2, 3, 4, 0.01 meters squared. So, what's the area here? No, 0.02, because she has two hands.
Wow.
Yeah. Each 100 centimeters squared. 100. Yeah. So your answer is 20 divided 20 divided by 0.02 is 1,000, which is 1 kilopascal. Gotcha. Yeah.
2 hands.
Yeah. 2 hands.
What about 3 hands?
3 hands. Or what about 1 hand?
Yeah.
Yeah. True. We'll imagine 2 hands for this woman, not 3 or more. Okay, continue. Yeah.
My answer is right for all.
Your answer is right for 1 hand. Wrong for this, though. Okay, I'll let you try these for a few minutes and then we'll start the next lesson. As you can see, they're not very difficult, so you should get them finished in 5 minutes. Coal. You know coal? You put it in the fire to make fire. It's black. Small and black. Oh, come on. It's small, it's black. You put it in the fire to make fire. BBQ, yes.
Yeah.
Use coal in the barbecue to make the fire. You know it? I'm sure you have it in Vietnam.
Yes, I have.
Good, okay.
But in chemistry, it's
Charcoal.
Charcoal.
No,
Yeah.
In chemistry,
Carbon?
Yeah.
It doesn't matter. It's coal. Anyways, it doesn't matter for the question. It could be 20 kilograms of apples. It doesn't matter.
What's the distance in this question? It's not 4.
A woman pushes 20 kilograms along the ground a distance of 4.
Yes.
I'd say the distance is 4.
Yeah, it's not clear there. Look,
Oh, I see. Let me fix that so. Maybe it's better?
Is this assuming that she has 1 foot or 2 feet?
How could she push something with 2 feet along the ground?
Jump.
Just picture that. You know what I mean?
Penguin.
It has to be 1 foot on the ground and the other foot pushing it. What? What, Lee? What? What did you ask, Omar?
No, he said there was also.
Yes. Just to be clear, she is pushing with 1 foot and not with 2. Do you ask questions like this in your other classes? Just wondering.
No, physics.
Yeah, I mean, yeah, I said, okay.
why we need the math?
You don't. You see, I put that in. Well, you don't. You don't need the mass.
see, the speed that is not changing. Speed will stay the same.
How could we I swear to you, I know that's the area of the circle.
Pi r squared. Finished, Faisal?
No, not yet. That's all.
At this point, you should have question 1 and 2 finished. Fuang, which question are you doing?
2B.
Okay. Nearly finished, yeah?
To
Yes.
area.
Yes? Of what? Of what? What shape? Circle. Ask him.
Pi r squared. Pi r squared. R is given.
Okay, let's have a look at the next lesson. So, finish that for homework, okay?